Last time we talked about how to draw a graph and how to embed a graph. That is, we gave a technical definition of what it means to be a drawing or an embedding of a graph, especially thinking about the plane. Right? It was just a continuous, drawing was just a continuous map from the geometric realization into the plane or whatever space you want to do the drawing. And the embedding is just a drawing that's injective, that is no crossings. All right. And I told you that there were these two graphs, this K5 and K33, that if they're somehow hidden inside your graph, then the graph is not planar. And in fact, if your graph is not planar, then it has one of these graphs somehow hidden inside it. We're going to prove that theorem eventually, but today we're going to talk about first, in what sense can one graph kind of hide inside another? We've seen one sense, which is just being a subgraph, right? It could have K5 as a subgraph. And I'll bet you could work out that if a graph has K5 as a subgraph and K5 cannot be embedded in the plane, then that graph can also not be embedded in the plane. But there are other ways for a graph to kind of hide inside another graph, and we're going to talk about that today. So let's get into it. The topic is going to be topological minors, and here's the starting point for thinking about this. You see, we can have two geometric realizations of two different graphs that are homeomorphic, so they're topologically the same, but it doesn't mean that the graphs were isomorphic. We did prove the opposite direction, right? We proved that if the graphs are isomorphic, then their geometric realizations will be homeomorphic, but the converse is just not true, right? And the simplest example is this case of two paths, right? The path of length 1 and say the path of length 2. Let's draw them. And so here's a path of length 1, here's a path of length 2. These two graphs are not isomorphic, but their geometric realizations are homeomorphic. That is, these two paths are topologically equivalent. So what can we learn from this? First, let's just check that we really believe this. I can show you that they're homeomorphic by explicitly writing down what the homeomorphism is. So let's call it f. So let's have this function, let's call it f, and it should do the following, right? So I'm going to go from here to here, from P1 to P2. Actually, this is from the geometric realization of P1 to the geometric realization of P2. And what I'll do is I'll take the midpoint here, and I'll just map it to this first vertex, and I'll map this vertex here, and this one, let me just get it all the way over to here. That makes sense? So I'm kind of like taking this line segment, doubling its length and laying it on top of this other one. Formally, that's not too hard to write down what this function should do, because the domain of this function is one line segment. So right, this is B0, B1, then this is taking a point 1 minus t B0 plus t B1, and right, so that's how we parameterize the line segment, so every point in the domain is of this form. And we're just going to map it to, well, two cases we should consider, right? First, I'll just write them out here. If t is less than or equal to 1/2, and if t is greater than 1/2. Let's write it like this. And actually, I'm going to do something that will intentionally make you uncomfortable, which is I'm going to write this as follows. And that's usually a really bad thing to do, because if you're going to define a function by cases, then you have to make the cases disjoint, and I've overlapped them at exactly t equals 1/2. But I want to check that this is continuous, so I'll just write it this way so we can check that when you see that the cases are not disjoint, you need to check that they are equal there, and that will tell us also that the function is continuous. So here's what I want. I want to take from 0 to 1/2, I'm going to double out the length, and then I'm going to pick the corresponding point on the first line segment. Because when I get to 1/2, I want to get all the way to the end of this first line segment. So this will be 1 minus 2t, that's the doubling of B0, plus 2t times b1. T in this case, since it's between 0 and 1/2, that means 2t is in between 0 and 1, and this is also between 0 and 1. So this is a line segment from b0 to b1. And now we want the second half of this, if t is greater than 1/2, to map to this line segment. And so you can check, I'm pretty sure this is right. If you do 2 minus 2t times b1 plus 2t minus 1 times b2, right? So this is really me just taking the numbers from 1/2 to 1 and remapping them to be from 0 to 1, so that I can take this line segment from b1 to b2. And at t equals 1/2, this is 0 plus 1 times b1, so that's exactly b1, which is what we wanted at the 1/2 mark. And at t equals 1/2 here, this is 2 minus 1 is 1 times b1, and 1 minus 1 is 0 times b2. So this is also equal to b1 at t equals 1/2. All right, so this is a continuous function. You can check that's actually, it's linear on each part, and so it's a continuous function that maps me from the geometric realization of p1 to the geometric realization of p2. It's not too hard to also write down the inverse of this. And so we have a function, a continuous function with a continuous inverse, and it's bijective, and so we have the isomorphism. Okay, so this is kind of formally writing down what was visually obvious, which is that, if I have a path and I have a path with a bend, that they are going to be topologically equivalent. And so we're going to push on this idea of taking paths and sort of adding extra vertices on the path as a way of getting new graphs which are topologically equivalent. All right. And I think I'm going to introduce this vocabulary, which is a very slight abuse, but it's quite common, which is we'll say that two graphs are homeomorphic if their geometric realizations are homeomorphic. Okay, so P1 and P2 are not isomorphic, but they are homeomorphic. And that, of course, always just means in terms of their geometric realizations. And because we saw last time, this also means that it doesn't matter if we take any drawing, or any embedding rather, of the graphs, they'll still also be homeomorphic. All right, so let's take this example. Here is a graph, and G, and it does not contain a K4 subgraph. You can check, it's just not there. But there is some sense in which it seems like it's got a K4 in it. And here's what I mean. If I kind of circle some of these vertices here, and I were to kind of glue together these edges and these edges and these edges, all these paths going around, it looks like I found K4 hiding inside my graph. So in what sense does G, let's put this in big scare quotes, contain K4? It's not in the sense of a subgraph, but we can do the following. We could take K4, we can subdivide it. So let's, that is, we're going to take an edge and replace it by two edges. So here, if I replace this edge by 3, that's really me like first doing 2 and then splitting again, right? So I'm splitting and splitting and splitting. And if I do this a bunch of times, I keep splitting edges, the result is a graph called a subdivision. Right, so this graph H here is a subdivision of K4. So this first step here is subdividing. So we subdivide the graph, and then after we've subdivided it, we can include it, that it is a subgraph now. Right, so there is this injective map from H into G, right? It hits part of G, it doesn't get this spoke here. But this pair of operations is going to be the defining feature of what we're going to call a topological minor. That is, we're going to take a graph, if you can subdivide it and then include it into G, then it's a topological minor. Right? So formally, G is a subdivision of H if G is formed from H by subdividing edges, and I should just be clear here, I mean 0 or more. So that allows us to say that a graph is a subdivision of itself. And here's a nice exercise that you might want to stop and think about a little bit, or write down and work on after we do this, is that if G is a subdivision of H, then the geometric realization of G is homeomorphic to the geometric realization of H. This is like the extension of the case we did where we took a path of length 1 and replaced it with a path of length 2. And the way you would prove something like this, I think, would be to do it one edge split at a time, one splitting or subdividing one edge at a time, and applying or constructing a homeomorphism for each step similar to the one we did for the paths. All right, it's not too hard an exercise, but it's worth doing if you want to get your head around these definitions a little better. All right, so if I have two graphs that are homeomorphic, then I claim there exists a graph that's a subdivision of both of them. So I might not have these two graphs themselves might not be isomorphic as graphs, but I can at least find some common subdivision of the two. And so here's an important fact. Again, this one you can work out using points at topology, but if you're going to have some homeomorphism between two graphs, it's going to have to map degree k vertices to degree k vertices as long as k is not equal to 2. Right? So that means, like, if I have three edges coming out of a point, any homeomorphism, no matter where this goes, is going to have to map it to a point with three edges coming out of it. So other than the degree 2 vertices, this homeomorphism is going to map the vertices to vertices. We don't know what happens to the other ones. And so we're going to say that a path is a degree 2 path, let's call it degree 2, if the internal vertices, that is not everything but the start and the end, the internal vertices, and only those, mind you, are degree 2. So obviously in the path they're degree 2, but what I mean is that as a subgraph, the vertices along the path are only have degree 2. In pictures, this looks like the following. So, so if I have this graph, I can have a degree 2 path like this, okay, which starts at a degree 3 vertex and goes to another degree 3 vertex, and everything along the way is a degree 2 vertex. Now, the fact that the non-degree 2 vertices get mapped to between each other bijectively from F really means that F gives us a correspondence between these degree 2 paths. So if I take the degree 2 paths in G, they map through F to degree 2 paths in H, as their images are now homeomorphic. So once we have that, we're going to construct this common subdivision. Remember, the goal is to show that there exists a common subdivision of both. We'll construct it in the following simple way. Right, we'll prove it exists via a proof by construction. So we'll construct K as follows. We just start with G, and then for every degree 2 path, we're going to subdivide it until it's at least as long as the corresponding path in H. So if the degree 2 path in G has more pieces, has more edges than the one in H, then we won't need to subdivide it at all. But if H has more edges in the corresponding path, then we'll just subdivide it until it has at least that many. So this graph that we've constructed is clearly a subdivision of G. We sort of explicitly built it to be a subdivision of G. And you can check that if you were to do this operation in the other direction, that is starting with H and subdividing it, you would end up with exactly the same graph. So as long as the corresponding path in H. Okay, so I'll leave that last part for you to work out, but it's really just checking that this operation really does produce a subdivision of H as well. All right. So even if you don't have isomorphism, there is some common subdivision. Now, all right, this is the kind of the big picture. When I define topological minor, I'm going to do these two operations. Not just subdivision, but subdivision followed by inclusion. And that's how you get topological minor. Right, so this graph G is a topological minor of this graph H because H contains a subgraph, G prime, isomorphic to a subdivision of G. Here I wrote contains, but you should think of this contains again as up to isomorphism. So I will just stress this again, right? There's two steps to be a topological minor that you kind of first subdivide and then you include. And if you want to, maybe a wonderful example of this is that you can redefine what we called a forest just in terms of topological minors. So recall that a forest is a graph that has no cycles. Right, there are no subgraphs isomorphic to any cycle. But here we can show that it's enough to just say that it doesn't have any C3 topological minors. So there's no subgraphs isomorphic to a subdivision of C3. First thing you want to check is that any cycle is a subdivision of C3, for any k, at least greater than or equal to 3. I guess we didn't really define cycles for k less than 3. So any cycle has a C3 topological minor. And so if G has a cycle as a subgraph, some CK as a subgraph, then it also has C3 as a topological minor. But something stronger this is true, of course, is that, in fact, the converse is also true. So if it has a C3 topological minor, then it must have a cycle subgraph because all subdivisions of C3 are cycles. So any subdivision of C3 is a cycle. Okay, so this means that the graph is going to have a topological minor if and only if it has a cycle, and therefore it has a C3 topological minor if and only if it's a forest, which is exactly what we wanted to prove. And so what's interesting about this example and the corresponding result in the corresponding new definition of a forest is that we only had to restrict ourselves to one graph. Whereas before we said the forest doesn't contain CK for any k, now we just say it has no C3 as a topological minor. So we defined an entire class of graphs in terms of what topological minors are forbidden. And in this case, we now only have a constant number of graphs that we want to forbid. And that defines our whole class of forest. There's going to be a bunch of other classes of graphs that we can define just in terms of which topological minors they don't have. Okay. And when I say here constant number of graphs, I mean graphs as topological minors. All right. So you probably have guessed now at this point that as I've defined these two graphs, these K5 and K33 as important graphs for planarity, it is going to turn out to be the case that a graph is planar if and only if it doesn't have K5 or K33 as a topological minor. And we'll actually prove this, and we'll see other kind of notions of minors. But in general, this is like a powerful idea that you can characterize important properties of graphs just in terms of what structures are not hidden inside them. And this idea of forbidding certain structures is a way to construct a whole bunch of different interesting classes of graphs.